So for the chapter 16, we are gonna to talk about mixed strategies. And the example is about tennis. Now, there are a server and a receiver. The chances of the server to shoot left is a quarter, and the chances of the receiver to defend on left is three quarters. So if the server knows this, he would like to go to shoot right, but again there will be a loop if you think about the possibilities. So there is no Nash's equilibrium because each scenarios, each situations, the server or the receiver can take another choices, another strategy to maximize their payoff. So that is no, in these circumstances, there is no Nash's equilibrium. No pure strategy Nash's equilibrium. What is pure strategy? There are two principles. The first is we can say a player plays a pure strategy if he plays a specific strategy. If he plays a specific strategy with certainty, like the server always shoot on left, the the receiver always defend on left. That is a pure strategy. The second is notice there is no pure strategy to randomize to no pure strategy Nash's equilibrium in the game of tennis. Yes, because you can't just simply decide to shoot on left all the time, and it is easy to be defended right. So there is no pure strategy in this game. Let's allow each players to randomize strategies. So what is mixed strategy? It is a pool of possibilities. That is, a mixed strategy is a probability distribution over all visible actions of a player. For any finite game, at least one mixed strategy Nash's equilibrium exists. It is called mutually best responses. What is the best probability distribution? So let us begin to analyze this game. So we divide the possibility P if P is and P and Q. If P equals to 1, then shoot left, and if P equals to 0, then shoot right. If P is half, then it is half left plus half right. The best response and analysis. For receiver's problem, the arrow is left is 3/4 P plus 1 minus P multiple a quarter. It is a quarter plus half P. And for R, we know that the R's problem, there are, yes, we know that is like a quarter possibility to play R. So the R is a quarter P plus 1 minus P, and 3/4 multiple 3/4 is it is 3/4 minus half p, and we can just write the number in a chart for receiver. So when p equals to 50, and whether left or right is best response. If p is greater than 50%, then LO is the best response. And if the p is smaller than 50%, then choose to defend right is the best response. Okay, we know about this, right? So for the server's problem, and I'm just not to say the full function, jump into conclusion. So we can just draw the same chart, and we can find the server's best responses line. And the server's best responses line and the receiver's best responses line have an intersection. The intersection is mixed Nash equilibrium, and it is P equals P and Q both equals to 50%, and it is unique because it is only a simple Nash's equilibrium. Yes, a simple intersection. So that means in the tennis game there are some, the Nash's equilibrium is 50%, so that is for the receiver and the server, whether you choose to shoot left or shoot right, it is the same. It brings the same profit, right? If that is very comprehensible, because if you have a specific strategy, like you also to shoot left, then the receiver always defend left, it is very easy to be defended, right? So yes, it is about mixed strategy. So how can we test theory? When people try to generate random sequences, they generally switch too often to be consistent with randomly generated choices. That is, even though the first the server first ball is left, and the second ball is left, and the third ball is also the left, it is very randomized, right? Because each round it is 50% for both left and right. But we always think it is, if we encounter 3 left ball, we are more likely to predict the next ball is right. So for these circumstances, we are switched too often. That means we don't want to be predicted in this situation. So it is about the example of tennis game. It is the end of the chapter 16. Thank you for listening. See you in the next video. Bye bye.